All right. Great to see so many people showing up for a security talk. I'm really happy about that. First of all, who am I? My name is Erlend. I work at a company called Blank in Oslo. I spend most of my days as a developer, but also do a fair bit of security stuff like security testing, some bug bounty hunting, and also am the main author behind Retire.js. And I'm the head of the OWASP chapter in Norway. When I first created this talk, I was thinking a bit about the OWASP top 10, because a lot of people know the OWASP top 10. And I was doing a bit of bug bounty hunting, reading quite a lot of bug bounty reports, and I started to see this thing where a lot of the bugs that people would find in bug bounty program were not a part of the OWASP top 10. So there were a lot of new types of bugs that were appearing. And I thought it would be interesting to bring this out to everyone, because there aren't that many people that are as interested in me in security that they troll through all of these reports all the time, although that's very useful to do. So some of the things I'm going to show you are kind of a part of the OWASP top 10 because they've kind of been included eventually, or parts of them have been included. But I'm also going to show you things that aren't, and I'm going to quickly move outside of the OWASP top 10. I'm also either really brave or really stupid, so I'm going to do some demos, which might fail, but they usually succeed, and I hope they will today as well. If we go to these bug bounty platforms, this is some statistics from 2018 from BugCrowd. And one of the things we see here is cross-site scripting. You can see them in orange and in purple at the bottom, that this is a very prevalent bug. And this matches pretty well with the OWASP top 10. We also see server-side injection in the blue, which matches the OWASP top 10 A1. If we go to HackerOne, which is another platform, this is their 2019 statistics. We see that they've divided it by industry. So we see transportation all the way to the left, and we have healthcare, and we have telecom, and travel and hospitality, and all kinds of different industries. Again, we see cross-site scripting as the most common problem that we see there, but we see a lot of other things popping up as well. One of the things that I briefly mentioned that I like to do is to follow these bug bounty programs and see the reports that come out of them, because a lot of bugs are, they publish the reports. So someone reports a bug, they fix the bug, and then they publish it. So, and some of them have a lot of details about how the attack went on and how it was performed, and some of them are redacted, so they give very little information. But quite a lot of them are things that we can learn a lot from. We can either follow the disclosed H1 Twitter account, or we can go directly to HackerOne and go to the activity page. We'll see the same thing there as we saw on the Twitter account. This is just a Twitter account that's tweeting the same thing that you see here. If we go to one of these reports, this is one that I reported to HackerOne in a Node.js library called Samlify, which is a SAML validation library, where they had what's called a XML signature bypass. So I could basically be whoever I wanted to be and bypass the validation that was in that library. And so there's a description here that describes how I went about doing that. And that, I've already mentioned SAML. SAML is XML, and XML is so much fun. XML can do so many weird things. We think of XML as a markup language, but the parsers of this markup language, they are weird and funny and scary. So we have this little application. This application here, we have the request up here. This is the request. And when I hit the send button, I get the response down here. So if I send this multiple times, you'll see that the ID down here is changing. So it's increasing. I can send this. So I'm actually sending these requests from my slides. And we can get one of these. I'll get the one with the ID of 1. So I'll get the first one, and it looks like this. So there's nothing in the request, but there's something in the response in this case. And then we have XXE. This was now a part of the OWASP top 10 that came out in 2017. And what we can do with an XXE is we can define entities. So I've defined an entity here called content. Content is a system entity which will contain the contents of this file. And then I will use this entity down here. So now it takes the contents of this file, puts it into a variable, and then puts it as a part of the XML. Oh, wow, I can read files. That's fun. But then Java is very permissive. So instead of file, I can just do dot. That lists all the files in the folder I'm in. That's useful. You do slash, gives me the root. But back to dot. There was a file there that seemed interesting. This one. I want that one. Summer 2018. Very common password. So this is why this is super dangerous. We can basically read any file. There is a limitation. It has to be, the end result has to be valid XML, or else the parser will say, hey, yeah, I got something, but I can't parse it because it's not valid XML. One other thing that we can do is we can use XSLT. So we can use XSLT to transform an XML into a different form of XML or even HTML. So in this case, I can send in an XSLT, and I can transform the first contact that I created into HTML. So you can see this is HTML, body, table, very simple HTML down here. And of course, XSLTs, they have functionalities as well. So we can start to query things like system properties. So if I'm an attacker and I can control the XSLT, I can start to query the system. So in this case, I can figure out what version it is. So this is XSLT version 2. And that's very useful for me because we'll see in a minute that it has some functionality that I really like as an attacker. And we can also see like the provider and things like that. So the first thing we can do is we can use a function called document. Now, document in XSLT allows us to take an XML and include it in the current XML. So in this case, I'm going to read out POM XML, which is the Java or Maven descriptor of this application, and I can see all the versions of things that they're using. So maybe they're using a vulnerable library of some kind that I can attack later. But I can read out any file that's an XML, basically. I can also do XXE in the XSLT because the XSLT is also an XML file. So I can do the exact same thing that I started out with. I can include this etc password file into the XSLT result, and then I get the same file. Now, in XSLT 2.0, they included a new function called unparsed text. And this is great because now it doesn't have to be valid XML anymore. Now I can include any file. So it works the same way as document. Grabs the contents of a file and puts it in the XML. But I didn't mention one thing. System entities don't have to be files. You could kind of see it that I had it like file : / blah 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 in the first version there. We can query the local network. So we can go around figuring out which ports are open. So in this case, I'm going to another server that's only available from inside the network. And it's running on port 9200, and this is an Elasticsearch instance. So I can now reach this Elasticsearch instance through the XML parser. And I can sort of map out the internal network. I could do port scanning. I could do things like that through this bug. So it's super dangerous. Sometimes we can't see the result of the parsing. Maybe it's parsed later. Maybe we post the file in, and some time later, minutes, hours, or just seconds later, it's going to be parsed, but we can't see it. We can get the parser to send us the file instead of just showing it in response. So what I'm doing in this case, in this example here, is I'm defining a, let's say, a variable that can be used in the DTD that's called data. And data will contain the contents of this file. And then I'm going to grab a DTD from an external source that I control, which is down here. And I'm going to also include the contents from that file down here. And then this one defines a new entity called external entity, which I'm including down here. And in that entity, I'm using the data variable all the way from the top. And then I'm going to put this entity down here. So what essentially happens is it does all this parsing and grabbing and stuff, and then it calls the URL down here with the data extracted up here. So I can get it to send me the file via an HTTP request instead of having to get the actual response back. And there are many ways of doing this. There's a really good resource on GitHub that explains this for various different parsers. So this is an example from HackerOne from Twitter. They had an XXE bug. And as we can see, Twitter paid $10,080 for this bug. even though it was only rated as a medium bug, but that's quite a decent sum of money to report one single bug. But that's because it is really critical. So how do we stop this? Well, we can disable DTD support. It really depends on the parser. We can disable DTD support, we can enable so-called secure XML parsing, and we can disable external entities. So OWASP has created a cheat sheet where we can see some of these things. But in .NET, luckily, they have disabled this since version 4.5.2, and you'd have to re-enable it for it to work. But in Java, there are so many ways that you have to disable it. You think you've disabled it, and then it doesn't work. So what I suggest, write a unit test that tests your parser and checks that it's actually disabled, and you don't just think that it's disabled. Because I've had this happen multiple times where I think I've disabled it, and it wasn't disabled after all. Sorry? Use regular expression for parsing the XML. Well, I wouldn't do that. Next thing, binding and serialization. This is also something that quickly can go wrong. When we're doing serialization, we're taking an object of some kind and we're serializing it down to a format that we can transfer or store. So JSON is an example of this. We have a server-side object, a Java object, or a .NET object, and we transfer it to JSON so we can send it either to a client or to a database or whatever. And then later we deserialize it. We take it back from this storage or transfer format and back into an actual object. And we use this everywhere. We use this in RPC, we use this in all kinds of wire protocols, web services, message brokers, caching, etc., etc. This is something we use everywhere, even in JOTs. Like that's also a form of serialization and deserialization. So we can imagine it looks something like this. So serialization, we have this JSON writer class. We give it an object and say, write this object as a JSON. And then when we want it back, we specify the type, and we specify the data, and we say, I want a type of object back. But usually it is not as simple as this. This is the way we kind of think it would work, and that's fine. But let's say we have this class, with this class called person. And person has a name, and if we serialize and deserialize this object, nothing bad happens. I mean, it has a name, it has a single property, nothing bad. But then we have this other class, which is not intended to be a part of the API. But if we were able to instantiate this class, if we were able to run the constructor of this class, it would actually start a process. So this is bad programming, right? We shouldn't have like things that happen in the constructor like this. But there are gadgets like this around. So a gadget is something we can use for deserialization attacks. So this is a really simple example. We can imagine then if someone sent this XML here, this JSON here, or this XML here, where you can specify the type. And this is the thing. If I can specify as an attacker the type that I want to deserialize to, then I might be able to find one of these gadgets. So here it's the $type, which is common for JSON, and here is type equals, which is common for XML. Now, usually it's not as simple as having a single class. Usually we have to combine gadgets. So this is an example from the presentation framework for .NET. So in this case, we have to create something called an object data provider, which again creates a process which takes some arguments, in this case the calculator, and runs the method called start. A very convenient thing, right? We can ask this object data provider to create an object of a specific kind and then run a method on it. So, but of course, this would be terrible. And this is from a library on GitHub called wysoserial.net, where they have a lot of these gadgets for .NET. And there's also wysoserial, which has other gadgets for other languages. But I promised you demos. So in my first demo, I'm going to create a process. And I'm going to create a process through something that Spring has that's called a dynamic proxy. So I'm going to tell Spring, hey, I want a dynamic proxy of this contact object that I normally create. So this is the exact same application that I used to begin with. I want to create a dynamic proxy which has an event handler which actually starts the process. Now I click the send button, I get a 500 error back, right? Bummer. But if we look all the way down here, Java lang Unix process cannot be cast to Java lang string. So maybe we were onto something. But I mean, pinging something? Boring. Let's hack it. So in this case, I'm going to start a shell. And I'm going to pipe that shell back to my hacker box that sits here. So dev tcp evil.hackers/1337. That's going to contact that. It's going to send the shell to that host name on that port. So of course, we have to listen on that port. So let's do that. Start a listener on that port. And we send the payload. And now I have a shell on that box. And I'm root. Yay! So I can do anything. I can do ls. I can do whatever I want. Poke around the server. Here's an example from HackerOne from Starbucks, where someone found a deserialization remote code execution bug in their JBoss MQ instance. It doesn't say how much money they got, but at least it says it was critical. Underlying cause, well, we allow the client to specify the type, and we allow the client to instantiate dangerous gadgets. So this is something you don't want. If you want to allow the client to specify types, at least you have to constrain it to certain namespaces or packages. And maybe they should have specific annotations or attributes to be allowed to be a part of deserialization. Or you could just disable specification of types. Also keep your frameworks up to date. Jackson, the Java JSON framework, has had a lot of these bugs, so keep them up to date. Next one is template injection. Template injection is kind of a part of OWASP Top 10 A1 injection. It was kind of snuck in at the last minute. And template injection is about these templating frameworks that we're using. So we have all of these frameworks that we're using for creating HTML or XML or something else. But let's go with HTML for now. So on the server side, this could be like Razor for .NET, or Velocity, or Jade, or ERB for Ruby, or whatever. It could be any one of those. On the client side, on the other hand, it could be React or Angular or Vue or some other templating framework that allows us to generate HTML from some type of data. So a simple template could look something like this. So we have h1, a tag, and then we have these curly braces and a variable. So this would take the contents of the variable and insert them into there. And it often, at least in the first versions, it was implemented something like this. So you would take this, you would tokenize it into h1 start, h1 end, and then you would do eval on the thing in the center, like the template itself in the center there, and get the value. And that worked perfectly. So if the title was hello, and the template was this h1 thing, then the end result would be h1 hello. Perfect. That's exactly what we want. The problem occurs once we start to use components, and we start to have multiple of these templates, and we sometimes put one rendered component into another component, like in this case. And you see the ... This doesn't have to be so close in vicinity in the code. Like this might be different function calls, and it might be so you can't really see what's going on. But just to keep it simple, we have these right next to each other. So we have we render one template with some variable, and then we put the result of that into a new template, and this is where it goes wrong. So because it works. If we test it, like, oh, hello and world, it's going to work. So the end result of the first one is going to be h1 hello h1. And then we put that in the second template, and we render that, and it's going to be hello world. And it's going to look like everything works as expected. The problem happens if the first variable contains a template in itself, because then that template actually gets rendered as a part of rendering the second template, because we're double evaluating the first template. So we take this title thing and we insert it in, and we can see the end result sitting in header now contains a new template, which is then rendered in the next line. And I mean, in this case, what 2 times 2 equals 4. Well, that's not that bad. We can do math, but we could do a lot worse. So here, once again, we have an application. In this case, you'll see the rendered HTML in the top frame and the raw response in the bottom frame. So I send in my name, and you can see it rendered as hello Erlend, and you can see down here h1 hello Erlend. So if I change this to, let's say, Øredev, we see it says hello Øredev in both places. Nothing special about that. Then I send in a template. Now it says hello 6. We can see the rendered result says hello 6, but it also says 6 coming back from the server. So obviously, this template that I specified in the URL was somehow executed. So we can start to poke around and try to figure out what is this templating framework that's running here. And I do _self in this case, and I'm suddenly shown this error message that says, recoverable fatal error, twig template, environment.php, aha. And it says evaled code. This doesn't sound so good. So obviously this is PHP. It's using a framework called Twig, and I'm able to inject stuff into it. What can we do with that? Well, we can register a filter called exec, and then we can specify the command that this filter will run, which in this case is ID. So it just runs the ID command on Linux, which returns the current user. But boring, yes, we want to hack the server. So we do the exact same thing that we did for the deserialization attack. We create a shell, pipe it back to our beautiful hacker box down here. So we listen on port 1337, we send in the attack, and I'm now on the server as this user, and I can poke around and do whatever I want. And you can see the minute I did Control-C to terminate the shell, yeah, it actually returned back here. We can do that once more. Send, and it's waiting and waiting, and when I do this, you can see it kind of blinks, because then it actually returned the HTML response. It was waiting for this process to finish. Eventually it would rather time out, but yeah, I'm in the server if I want to. But this was server-side. So we could see the 6 was coming back from the server when I sent 2 times 3 up here. What about the client side? So in this case, it says 6 up here, but here, down here it still says 2 times 3. Why is that? Well, in this case, it's because we have Angular involved. So Angular sits here as a library, and I have ng app here. So this thing is treated as an Angular template. So Angular will pick this up and say, hey, there's a template here. I'm going to execute it, and then it's going to return 6. So the immediate thing we think, we can do cross-site scripting now. We can do alert 1 and see if we can get that going. But then nothing happens. That's weird. Well, that's because Angular used to have a sandbox. And this sandbox was supposed to disallow you to run arbitrary JavaScript. You should only be allowed to run certain types of JavaScript. The kind of JavaScript where you got your data out and things like that. Unfortunately, this sandbox was broken multiple times. And this is one way to break this sandbox in that version. So what we do is we take a string, and we take the constructor of string, which is the string constructor. And then we take the constructor of the string constructor, which is a function. And we take the function constructor, and we create a new function with alert 1. And then we invoke that function. Boom, alert. And it comes 2 times as well. So this was a way to bypass that sandbox. And this was going back and forth for a long time. There were some really great security researchers that was kind of messing with this, and then the Angular guys fixed it. Then they found a new bypass, the Angular fixed it, and it was going back and forth up to at some point where Angular just said, well, we're actually just going to remove the sandbox, because this is not the way Angular is supposed to be used. You're not supposed to be, as an attacker, be allowed to specify your own templates. But this happens because we sometimes mix server and client-side templating. Here's an example from Rockstar Games. They had a Angular injection, and this paid $1,000 to the person who found it. So how do we discover this? Well, we can try different types of templates in all of our input fields, like the double curly braces and dollar curly braces, percentage curly braces, etc., etc. We can try generic things like 2 times 2 or 4 minus 1. Do not do 2 plus 2, because if it's a part of a URL, 2 plus 2 will be 2 space 2, and that will probably fail. So do 2 times 2 or 4 minus 1 or something like that instead. As you saw with Twig, I did _self, so that was a known construct in the language that I could use to kind of provoke an error. And we can use this as seen for cross-site scripting, or even for remote code execution and getting a shell on a box. How to stop it? Don't double evaluate templates, and don't mix server-side and client-side templating. That's when things go wrong. And keep your frameworks up to date. That always is something you should do. Next thing, insecure cross-origin resource sharing. This is something we've seen a lot of lately. So we have this thing, access control allow origin. What does it even mean? Well, we try to, okay, so we want to allow other websites from other servers to access something coming from our server. So we asked Google Translate. It can help us. So we want to translate from HTTP to English. We insert access control, allow origin example.com, access control, allow credentials true. This is not possible, by the way. This just but then in English it will say, if the user is logged in and visits example.com, please allow that site to access the user's data. So we say, anything coming from example.com running in the user's browser can actually use the current session tokens, etc., of the user when it's talking to me, and you can display the data. And then we have this thing, access control allow origin star, access control allow credentials true. So if the user is logged in, please allow any site the user visits to access the user's data. This is a bad idea, and the browsers know. So they just disallow it. This is not an allowed combination. You're not allowed to do this. But developers are clever, and they think, aha, so that's not allowed, but I'm going to find a way to circumvent this anyway because I need this in my test environment, and then we forget and we push it to production. So what are the mistakes we make? First one is the echo. So we grab the origin header, and we just put that into access control allow origin. So if it's example.com, it will say example.com. If it's evil.com, it will say evil.com. So we've kind of reintroduced the star, only we've hacked it. Not a clever thing to do. This is one of the things that was discovered by a guy called James Kettle, who works out of Portswigger. And we've seen a lot of this in these bug bounty reports. Next one, insufficient validation. We grab the origin header once again, but now we're gonna be smart. We're gonna check that it ends with example.com because that's the only thing we want to allow, but we want to allow the subdomains as well. The problem is, though, that not example.com also ends in example.com. So this is broken. Last one is null. What null? What does null even mean? Access control allow origin null. What's the null origin? Let's ask Google Translate once more. Access control allow origin null. If the user is logged in, please allow any site the user visits to access the user's data as long as the site knows how to use iframe with the sandbox attribute. It looks like this. So we create an iframe, we set sandbox, allow scripts, allow forms, and then we run the Ajax call inside of this iframe. This gives us an origin of null, and we're allowed once again to read the data. This is again the star and true. Here's an example from Zomato.com. This is James Kettle, who I just mentioned, who reported this. And if we see here, ending in Zomato.com, including not Zomato.com. So this was the exact bug number 2 that I just shown. Next thing we're going to look at is something called server-side request forgery. Server-side request forgery is something that happens if we have a setup where we have, let's say, a browser or some other type of client. We have maybe HTTP, we're running some requests into a server application, and that server application, it runs HTTP requests towards some other application. It might be a backend service, but it could also be something online somewhere. The problem in this case is if the browser could somehow affect how the second HTTP request is formed or where it's going. So an example. So we have a request coming in from the browser that looks like this. example.org/images 200x200 product.jpg. In our server application, we try to replace the first bit. So we try to take away https example.org, and we add images example.org, then we go out and we do an HTTP request to get that and return that back to the user. So we strike out the first part, replace it with images, and then grab the contents and then return it to the user. Yeah, that works. All right, we're happy, we push it to production. And then this thing comes along. images.evil.com. Okay. So we strike out the first part, and we end up with this, images.example.org.evil.com. Okay. That's obviously not what we wanted. And now if this call to the backend service also included a username and password, this would now be sent to evil.com instead of where it was originally planned to go. We can even do more. We could do something like this. So in this case, images.example.org would become the username, And then dummy would become the password. And then what comes after the @ would be the actual host that we would go to. So it would treat this as basic authentication in some frameworks. Sometimes we have functionality like this. This could be to read in an RSS feed, to read in some financial data, whatever. So like we can specify the URL. That's a part of the functionality. And then we have to make sure that we don't allow dangerous things like this. So in this case, I'm going to go to the MongoDB that sits on the same server and just grab stuff out of there, which is obviously not what the developers of this application intended. Or sometimes these parsers also allow us to specify file URLs, and we can read files as well, which is handy if you have malicious intentions. But where this has really gone wrong is on cloud, because on the cloud, especially on AWS, you have this thing called the metadata host. You have this on other cloud provider as well, and it runs on port 169.254, 169.254, and we can ask it about things. We can ask it about like, what is this server I'm running on, and we can even ask it for keys and credentials for that host. So now, if I can from the outside ask it to return the contents of these metadata calls to me, I can get the keys to the host, and then I can just SSH into the host, which could be useful. And this has happened many, many times, actually. We've seen a lot of examples of people who have gotten lots of data stolen this way. But we could also, of course, go to other types of things like MongoDB or RavenDB or any other HTTP-enabled service. So we're going to be smart. We're going to blacklist the IP, because we don't like this IP. It's dangerous. What's this IP? 425.510.425? It's above 256. Well, a lot of these parsers, they will just do mod 256, and so it will become the exact same IP. These two are often equivalent. This is from a guy called Nicolas Grégoire, who did an amazing talk called Server-Side Browsing Considered Harmful around this topic. What about this thing? Well, that's a numeric IP. This is a numeric IP with overflow. A hexadecimal IP, hexadecimal IP without dots, with overflow, octal IP, octal IP with overflow. So these are all the same IP. They just look very different. We could do more. We could register our own domain name to point to, let's say, localhost. So we have evil.com. We register custom.evil.com to point to 127.0.0.1. But someone's done that for us already. They've created something called zip.io. So if I do 127.0.0.1.zip.io, that will always resolve to localhost. We can even base 36 encode it so it looks a little less suspicious, or even add stuff in front of it so it says www.bank.no and then the rest of it. Will still resolve to the same IP. So this is getting difficult. And then there's 0.0.0.0, which is all interfaces on the machine. And it doesn't have to be 0.0.1. It could be 127 4 times. And IPv6. Oh, yeah. And then there's a guy who calls himself Orange Sai, who did an amazing talk about breaking URL parsers. And he found this thing. Like, if you parse this on different machines, you'll get different results. On Windows, it will see it as a UNC path. But on Linux, it will see it as a file URL. So it will turn different things depending on the machine. So you can create like polyglot URLs to steal files. Amazing stuff. And then you have things like this, like Apache Tomcat things, the dot semicolon is the same as dot slash. And yeah, that breaks things as well. Here's an example. This is from HackerOne, and they found a bug in Alien Vault, and we can see the IP down here is 169.254, 169.254, metadata nicob.net, which is Nicolas Grégoire, who I just mentioned. So how do we detect that this is going on? Well, we can build an egress log. So we can say that any HTTP client that we have in our code, it's going to log all the calls that it makes and all the return codes and things like that. And this is good anyway, because we want to know what's clogging down our system. Are we doing a lot of HTTP requests? We could have timing. We could have all kinds of metrics to this if we want. But at least we'll know if it's trying to access things it shouldn't. We could have an outgoing proxy to ensure that we can reach other internal services. We can normalize the host name, resolve it to an IP before actually requesting it. So we can ask, what's the actual IP that you're going to ask before we do the request? And we could have local firewall words that says this application is not allowed to access 169.254, etc., because we won't allow that. Next, subdomain takeover. Subdomain takeover was something that at least partially was discovered by Franz Rosen of Detectify. I think there were some other people looking at the same thing at the same time, but he's credited for finding it, and he wrote a great blog post about this back in 2014. But it's still a bit of an unknown thing for most people. So what this does, it exploits what we call forgotten DNS aliases, CNAME aliases. So we have all these cloud services, and let's take Heroku as an example. They've actually done a bit to stop this thing, but let's go with Heroku for now. So we can create an application on Heroku. We will get our subdomain as a part of the URL, so or as a part of the host name. So it could be like øredev.herokuapp.com. But we want it to be øredev.com, not herokuapp.com. So we want to have a custom domain name. Same thing goes for other types of services like S3 buckets and things like that. We get these names and we kind of put things there and use them. And there are a lot of services that allow this, like GitHub, Heroku, AWS, Bitbucket, Squarespace, etc. And Detectify found over 100 different services that allow this. So we create an application, oasp.herokuapp.com, but we want this to actually run on our domain called example.com as a subdomain. So we go into Heroku and we configure that this application is actually going to have a domain name of oas.example.com. And then we go to our own DNS and we say, if you ever see oas.example.com, that's actually an alias or a CNAME for oas.example.com.herokudns.com. So instead of resolving it itself, it's just going to say, go to Heroku DNS and ask them instead. So we can imagine it look like this. The browser goes to look up os.example.com, talks to our DNS, which says, hey, you should actually go see this Heroku DNS thing instead. So we go over there, we ask, what's the IP for this thing? We get an IP back, and then we reach the service we want. And this works as intended. So yeah, we're happy, we get the results, everything works perfectly. And we have this application sitting there for some time, but then something bad happens. We're tired of this application. We don't need it anymore. It was for an event, and that event is over, and we just go into Heroku and we delete it. Done. But we forget to remove the DNS entry. So now we still have a DNS entry, os.example.com, pointing to Heroku DNS. So what the attacker can do is go in and create an application with the same name, and now the attacker controls our subdomain. So what can you do if you control someone's subdomain? Well, you can go phishing with a proper domain. That's much more likely to succeed if it actually is oasp.org instead of herokuapp.com. We can inject or steal domain-wide cookies, so we can inject our own session cookies to fixate sessions. We can use this for political stuff or for adult stuff or whatever. We could even create HTTPS certificates because we now own this subdomain. So here's an example of a subdomain takeover on S3 for Shopify. Here's another one from Microsoft where they had this domain they used for tiles. And the host that should deliver XML files, notification.buildmypinnedsite.com, only showed an error message. And a person figured that he could actually register this, and he would get all the traffic. And here's another example. It's a bit small text here, but it says simongrishky.has.hacked.prod2.uber.com. So this is from the certificate transparency log, and it stays there forever because this is the log that publishes all certificates that have been published by CAs. So this Simon Grishky, he was able to hack into prod.2@uber.com through a forgotten CNAME, and then he issued this certificate, and it stays there in this log forever. Last is something called web cache poisoning. And web cache poisoning was also discovered by James Kettle, who I mentioned a few times. Now, James Kettle works for Portswigger, which creates a tool called burpswit, which is one of the most common security tools that the penetration testers are using. And what James was trying to do, he was trying to exploit what we call unexploitable bugs. This could typically be bugs where you could only affect yourself, like a cross-site scripting where you could only inject things in your own browser. And cross-site scripting, you want to send an attack where you can attack someone else, but sometimes you have self-XSS. You can only attack yourself. And he wanted to figure out a way where he could exploit these bugs, even though it was sort of a self-XSS. So he did a lot of research on this and wrote a blog post and did a couple of talks around this. So we can imagine it looks like this. So we have our server, and we've set up this cache in front of it. This could be like an Nginx or some other type of reverse proxy with caching abilities. And we have a client that comes in. Now the client goes in and says, hey, I want this site. And the cache says, well, I don't have it, so I'm going to ask the server. And we ask the server, we get the data back, we store it in the cache, and return it to the client. So when the next client comes along and asks for the exact same thing, we're going to say, hey, we have this in the cache. This is exactly how a cache works. Perfect. So now we can save our server from processing the same things over and over again if we have a lot of clients. But then our malicious attacker comes along. And the attacker has figured out that there is a bug in the server. So he sends a payload, and the payload misses the cache and goes straight to the server. And then the result of this attack, where there might be a cross-site scripting or something like that, is stored in the cache. So we've poisoned the cache. So now when a benign client comes along afterwards and asks for the same thing, they're going to get the poisoned version. And the attacker can run cross-site scripting in the client that got the poisoned version. So nothing without a demo, right? So here is an application. I can send this in, and I get back this response down here. The important thing here is this thing. It says www.hackablenetwork/script.js. So okay, so it loads a script tag from this server. Now what the attacker has figured out is if the attacker sets this specific header called x-forwarded hosts and sets it to something that they want, the script tag will change. So now it says attacker.com down here. But in this case, we poisoned this URL, or maybe this URL. So it says t = 1. So if we go back to the benign client, it still says www.hackablenetwork down here. So we're going to remove this, and we're going to send it once more. But now it still says www.hackablenetwork. Why? Because we're hitting the cache. We haven't been able to poison it yet. And luckily it tells us that, well, the cache is valid for 30 seconds as a part of a cache control header. So we can just keep going. And at some point, we should actually be able to poison the root page without the parameter. There we go. That says attacker.com. But we're sending this header. What about the benign client over here? It also gets attacker.com now because we poisoned the cache. So now we'll see how brave you guys are. Bring out your phone or your laptop and go to this page and tell me what you see. I'm not going to do anything really bad, so no worries. What do you see? It's www.hackable.network. The logo of Øredev should be there. So it should look like this. Welcome, and then the logo of Øredev. So what I'm going to do now is I'm going to poison the cache. And all I'm doing now is I'm sending requests from my slides to the server, which sits out on the internet, and I'm trying to send this header, this extra header, to try to poison it. And so this is going to take the amount of seconds that the cache is valid, and hopefully I will be able to poison it once that cache times out, and then I should see a success message down here. This is the most dangerous of the demos because it might actually fail. Come on. I'm going to reload and try again. It worked earlier today, and that happens. Most of my demos, I ran them off Docker on my local machine, so I'm not too prone to bad things happening. But in this case, it actually seems that it have decided not to work. So we'll leave it there, try to hack, and then we'll come back and see if it works in a short while. So these are the headers that James Kettle found: X host, X forwarded host, X original URL, X rewrite URL. These were some of the headers that he discovered that different frameworks and servers, they were treating them as special things, where they would actually rewrite things that happen to end up in the cache. So things will end up in different places than you expect it to. So you could send in host, and it would grab that host and use that. You could set X forward host, it would do the same thing. You could set X original URL or X rewrite URL. And these are things that we normally use from, yeah, okay, so it worked. So if you now go back and refresh the page, it seemed that it actually worked even though it wasn't able to detect it. So it should look like, oh no, it didn't. It worked for some of you. Yeah, it worked for some of you. Yeah, you get Dr. Evil on your phones. Awesome. So it's just my browser that's messed up at the moment. Great. So it actually worked. So you get, what happens for those who didn't take part is that you get the image is replaced because it's using X forwarded host to actually replace the host that's loading the image, just loading it from somewhere else. And then you get Dr. Evil instead of the logo. Oh, it says success now. So now it should actually work. Yeah, so we have these headers. These are the ones that James found. And as I was trying to say, these are things that a proxy would send to the backend, so the backend would know what the proxy originally saw, because the backend might have a different URL than the front end, and the backend might want to know what the front end saw, or what URLs to put in their generated URLs in the HTML, for instance. This can be a bit complicated of an attack to perform because we have to know which URL parameters are used in the cache keys. As you saw, I had this t equals 1 thing. So it turned out that t was a part of the cache key, so I could poison one cache, and then I could then go back and try to poison the root. It could also be headers that are in the cache keys. So for instance, we could have different caches for Firefox and for Chrome, depending if we want to serve different contents for different browsers. But James Kettle works for Burp Suite, so he created a plugin for it called Paraminer. And I think this is only in the paid version of the tool. But this is one of the tools that you can use to find these things, or you can just go and review your cache config. How do we stop this? Well, we could block these headers inbound, right? There's no point in allowing a client to set the X forwarded host and X host head and all of those headers. Those are meant to be used from the proxy and towards the backend. So they shouldn't be coming in from the front end. Another way, which James suggested, was we could add those headers to the cache key. So if you have X forwarded host, you will actually get X forwarded host as a part of the cache key, and then a benign client wouldn't send that header and wouldn't get the poisoned version from the cache. But of course, in this case, we should also fix the backend server, which in this case just took a random URL and allowed that to be included as a part of the HTML. So fix your servers as well. We can use Burp Suite to also audit this. So Burp Suite, as I mentioned, is a really good tool. It's a paid tool. I'm not getting anything to mention it. I have no affiliation with Burp Suite. I just like the tool. So these are some resources if you want to take a picture. These are some resources that I mentioned. So we have the disclosed H1 Twitter account all the way to the top. We have Hacktivity on HackerOne as number 2 there. We have YSOSerial and YSOSerial.net, which are these deserialization attack examples. We have abusing XSLT for practical attacks, and we have template injection, which was also James Kettle. We have subdomain takeover from Franz Rosen. We have this server-side browsing thing from Nicolas Gregoire. There's the video of James Kettle's talk on course misconfigurations from OWASP AppSec on YouTube there, and also James Kettle's blog post called Practical Web Cache Poisoning. So just going to go back and see if it actually worked now. Yes, it worked. So that's what you're supposed to see. And that's actually it. On the bottom of the screen, there is a GitHub URL. If you want to play with the application that I've showed you, not for the cache poisoning, but for deserialization attacks and for XML attacks, you can download that app and run it in a Docker container and play with it. In the README file, you just specify the types of requests that you need to send in to test this. And if you want to add new stuff to it and help me build something that's completely broken, then go ahead. But never ever use that for anything other than fun. Don't ever use that as a working system and put it online. Just run it on Docker locally. Don't put it on the internet. That's it. Thank you.